Okay. The first thing that we're going to talk about is the symbolic logic that's going to be used. So in this text and in all of the lectures, P implies Q. So this is a statement P, statement Q. If P, then Q. And then the contrapositive is also going to be true. So if I say not Q, then that's also going to mean not P. So if P implies Q, then this is a logically equivalent statement. The converse is Q implies P. This is not logically equivalent to P implies Q. And in the event that the converse is true simultaneously, then we have P if and only if Q. And that is a statement of logical equivalence that way. There's going to be one caveat we're going to use for vacuously true statements. So a statement P implies Q is vacuously true if and only if there does not exist a case for which P is true. So the statement P implies Q can derive its validity from the fact that there will never be an instance where P is actually true. So one of those, a classic example of that is for the empty set. So if you have a set with no elements being a subset of a set A, and this tells us that X in the empty set implies X is also in A. However, there is no instance in which there is an element X inside of the empty set. And so there does not exist a case for this statement to be true, which makes the entire statement vacuously true. So we're going to try to, we'll address some of the set theory paradoxes with this definition. And then as a matter of notation for just sets and the differentiating between elements, sets, and the power sets, so sets of sets, then we can have, if I have a set A, and suppose I put A, B, and C in here, then that's going to tell me that I could express A as an element of the set A. I could also say that if I were to use the set notation, so then the subset with the element A in it is a subset of A. And on top of that, the subset, including only A, is then a member of the power set of A, where the power set's going to contain all of the subsets of the set A. That's the agreed upon notation for this text. So we're going to move on to functions. The construction of functions in this text is actually a little different than when we constructed. We constructed mappings, and those mappings were coming from two different sets. So then they allowed codomain, but here we're going to do a rule of assignment where the image is they're going to turn the range specifically into the image, so that you're not going into a codomain. But we need a preliminary definition here for this definition. So we're going to define something called a rule of assignment. So R, which is a subset of the Cartesian product between two sets C and D, we're going to call this a rule of assignment if and only if And we're going to denote logical statements by hard brackets. So if I want to contain statements that can imply other statements that involve implications, then there's no ambiguity between where the implications fall. So if I have the statement that CD is in the Cartesian product, as well as I have another point CD prime also in R, that this statement is going to imply that D is equal to D prime. So symbolically, this is representing that we have unique, for every single C, there can only be one D. And in the event that you have C going to D and D prime, those actually have to be the same thing. So there's no instance in which you can have one element going to two different elements. Another way you could say that with words is that every single element C is appearing as the first element of at least one ordered pair and only one ordered pair. So you would not have something like 1, 1 and 1, 2. That cannot simultaneously be true in a rule of assignment. So that would fail to be true for a rule of assignment R. So from this, we can actually then define domain. So then the domain of our rule is going to be a specifically defined set. So it's just going to be all of the points C where there exists one of these D, since it's this one-to-one correspondence, because this has to be unique to every single C. If we can find a D in the set D, such that if I put C and D together, then that can be found in the rule. We take the collection of all of those C's. So it's the collection of all the first coordinates that are allowed in the rule of assignment. That's what we're going to call the domain R. Before we get to functions, an image, the image of R, is then going to, instead of focusing on the first set, it's going to focus on the second set. So now we're interested in all of the D's, such that we can find a C in that first set that's then going to be paired together with our D in the rule. So there's the domain, and there is the image. Okay, and then we can use this to define function. So let's see if I can fit it under here. I'll try. So definition. So a function f, this is a rule of assignment R together with the set, together with a set B that contains the image set of R. And so this is how they're getting around using codomain, is because they're going to take the rule of assignment and then define image of R to be specifically these points. So they're going to turn the image into the range inside of a function, but with a different set B where the image can be contained by B. So you can have a codomain that's bigger than the image.
So B could be the codomain.
Right. So they're just not calling it a codomain. But algebraically, that's what they would do. So then the domain A of the rule R is also the domain of F. So that's the correspondence that is the same. They're going to take the domain of the rule, make that correspond to the domain of the function, whereas the image is going to be contained inside of another set B. That will be the codomain unnamed. Codomain. Okay. I think they do call, so Munkres is going to call B range relatively informally, but it's implied that range is still going to contain image. So he's making a distinction. Yeah, I think I'm going to ignore that. Well, because for the reason that he wants image to basically take the spot representatively of range algebraically,
Yeah.
and then he's using range as codomain. I think I might just stick with the algebra.
Yeah.
Because it's not really super important right now. Then, okay, we can get into the injections and surjections. So we can denote this F A to B. So I'm going to call this a domain. I am going to call this a codomain and to distinguish it with the image. Or image and range, those are the two terms I'm going to use synonymously. Okay, if this is a function, then we have that F is injective, if and only if. We have that F of A being equal to F of B can only be true if we have that. Whoops, I forgot to put this bracket there. If A is so every single point that you stick into the function is going to give you a unique function value. So in the event that you have corresponding function values, that's because you must have had the same input. This is, we call this one-to-one as well, more informally. F being surjective is going to be true if and only if we're going to have some element inside of the codomain. And that's going to tell us that if we have such an element in our, oh, well, no, they're technically using this as image. Now that I think about it, then there exists a B. We can find A at point A so that the function value at A is going to give you B for at least one of the A's in your domain. This just simply means that every single set or every single element inside of the destination is going to be covered if you are onto. So that would be where the codomain coincides with the image. And then F being bijective is going to be true if we have F injective and surjective simultaneously. So if we are both one-to-one and onto, then we have a bijection. Okay. And then there's two tiny little results here. So kind of these restatements, we can have that the statement F bijective, and this is going to be important for understanding inverse functions. That's going to imply that there is existing an inverse function such that the inverse of an element B gives back A, where F of A was defined to be B. And also, if F is bijective, that also is going to imply more trivially that the inverse is bijective. So if you can go with a one-to-one correspondence and cover everything in one direction, you'll be able to go backwards. This was interesting enough to talk about, so I'll actually cover it. So there's a little lemma. which tells us, okay, we're gonna have a function that goes A to B. So if we have that there exists some function that takes B to A, and another function that takes B to A as well, such that G of f of A gives back A, and that will be true for all of the A's in our original domain. And on top of that, we also, the same property will be true for the function h. So if I took f and I composed it with h of b, then that's going to return back b. And that will also be true for all elements in the codomain. Then we have a bijection. So f is bijective. And on top of that, so then these two different functions, g and h, are actually coincide. So where g and h are just the inverses, or just the inverse of f. And this actually, there's this definition. The one thing that was a little bit different that I think I understand why he renamed it term range instead of codomain is because he wants to introduce pre-image for having subsets in the destination. So I guess he thought that was going to be more clear than calling it. It still would have been fine, I think, to call it a pre-image from the codomain, but
pre-image is usually in the domain.
Well, image, so I think he's trying to use image as being going to the codomain, but he wants pre-image to be going the set that goes back into that, yeah. So if we have a function f, A to B, and then we're going to now take a subset of the domain. So we're not necessarily considering the entire domain. The image of the subset under F, we're going to denote it as this set. So this is also, I think it's Fitzpatrick adopts this notation where he takes the set, that subset, and it becomes all of the points B, where B can be found with F of A for at least one each element in that subset of A. And then if we have a subset in now the codomain, so B naught from B, then our pre-image of B naught under F, then we're going to define that from the inverse. So the inverse then of B naught will give us A's, where F of A, those are elements in that subset. These little refillable pens are really nice.
Oh,
yeah.
I've not seen them.
Because you can basically screw it out and then the cartridge is out. And just stick back in.
When did you discover those?
Austin, he showed
Really?
me these. He bought these for me for last semester. Yeah, because I was doing it for linear algebra.
So in that definition, F has to be a bijection.
Yeah, this is when F is a bijection. Yeah. Otherwise, it doesn't work because you can't guarantee you can go back.
Right.
Okay. Okay. I personally got more excited with the relations stuff because I think obsessing over what the equal sign is and less than sign is pretty exciting. So we have a relation Now there's a few different ways that this is notated, so I'll use like the typical, the letter abstraction before going over. So we have a subset. I shouldn't do that one first. I should do this one first. So we have a relation on a set A is a subset. And I'll notate this. We have some subset C of the Cartesian product of that set with itself. So then from the definition, it follows that if we have C a relation on A, then we can say that X relates to Y if and only if this particular pair, X and Y, are contained inside of C, because ultimately the relation is just a subset of the set with itself.
And the relation symbol is a C?
Abstractly. So they introduce it because they're trying to emphasize the fact that relations are actually subsets of a Cartesian product, but then we adopt then conventional notation, usually with a tilde between the, So this is the introduction of where we start moving the notation instead of representing everything like a rule of assignment. But it is nice. I do appreciate that because it shows it really all comes from exactly the same idea, just different variations. So specifically of interest, there's two kinds of relations. There's the equivalence relations and order relations. So an equivalence relation on a set A is a relation. And now instead of using the C, because that can get confusing, but I do like it to get used to it because then you understand the abstraction before the convention. But we'll use the tilde for convention. A relation tilde on A such that, and then there's going to be three very important algebraic things. So we've got X is relating to itself. So every single element needs to relate to itself if it's equivalent. So that needs to be true for every single X in your set. And we call this the reflexive property. So this is reflexivity. It's reflexive. Now, if we have it that it's true where X is relating to Y, we need this if they are equivalent to imply that Y can relate to X. We need it to go both ways. And that would be symmetric. So this is symmetry. And then the third important thing is it needs to be transitive. So that means if I tell you that X is equivalent to Y, and that Y then is relating to Z, again, with equivalence, then that should imply, if they're all equivalent, that X relates to Z. In other words, X would be equivalent to Z. This would be transitivity. So that was a fun little familiar face from algebra. And then from these things, because if we have now a way to relate things as equivalent, we can define equivalence classes. So an equivalence class, and they define the equivalent. I think Munkres did a better job of defining equivalence classes because Frawley, he kind of insinuated from partitions. So he tried to define the equivalence class from a partition, which is fine if you already know what a partition is. But learning it for the first time was tough. This is nice because then you just define a set E where the elements are contained as being the elements relating to in your set. So that was much more straightforward to go right from the definition into equivalence classes. And there's a pretty fun lemma that Frawley didn't include this one because that wasn't his focus. But it's basically saying that if you're going to have two equivalence classes, they can only be disjoint, or they have to end up being the same exact equivalence class. So practically, that means you can't have an equivalence class or two separate equivalence classes where then somehow they're sharing an element. Their intersection needs to be empty. Yeah. And then he uses that lemma to then motivate partitions. So that was kind of cool because then you think of the partition as being completely separate, and then it covers your original set. If you take the union of everything, that kind of follows more intuitively from that progression of thought. But so lemma. So we have two equivalence classes. So I'll just say equivalence classes E and E prime are either disjoint or equal. So, and then if we want to express this with just symbolic logic, we have E prime as equivalence classes. Then we want either them to be disjoint. So if we were to take their intersection, that needs to be empty. There can't be anything shared. And also, well, or they end up being the same thing. Okay, so we can actually prove this one. This is kind of fun. Let's see. Okay. So we're going to first show, obviously, if they're the same thing, then that's just how it's going to be. So what we're more interested in is this case. So we're going to suppose that we have the disjoint case. So they don't actually share any elements. And the idea is this not having any elements has to be this. So from here, where we need to be able to show that E is E prime. So if we have that Y is going to be inside of this intersection. And I'll draw a picture over here so that it's a reference for the outline of how this works. So if this is E and this is E prime, we're interested in this counterexample. So what if we're going to show that if they end up having some sort of intersection, then that's going to push all the elements over. So we're going to have some others, so a W, an X, a Z, and an X prime. Okay. So Y is going to relate to X. And the reason we know that is because it's in the equivalence class E. And on top of that, Y, because it is in this intersection, technically it needs to, by definition, relate also to X prime. Now, we can flip the order here because this is an equivalence relation. So if by the symmetric property, we can then say X, then relates to Y, and Y relates to X prime, so that by transitivity, we have that X is relating to X prime. So then if we have this other point W, so since we have W in E, then that gives W is relating to X. But if W is relating to X, we also have W relating to X together with X relating to X prime from over here. So now we have the issue of having W relating to X prime, which is supposed to be in E prime. And so we have that E is a subset of E prime. And so to show equivalence, we're going to show that E prime is then a subset of E through using another element, Z in E prime. So if we have Z in E prime, then you have that Z is relating to X prime by definition. And then if we have Z relating to X prime, because of symmetry, we can have that X and X prime relates to X. And then transitivity again. So Z is relating to X. And then once again, we see, okay, well, hold on, this is relating to this, which is going to force E prime to be a subset of E. And so now that we have E being a subset of E prime at the same simultaneously with E prime being a subset of E, then E and E prime are the same thing. So there's a fun exercise in relations, those properties. And then, like I'll throw this on here real fast too. So the whole idea where if you then take the union of all of the equivalence classes, then you should get back to your same set because they're disjoint. Although actually on second thought, now that I'm thinking about it, I think probably did include this, but it was an exercise, not example. And it's definitely not in the text portion. I would have recognized it. But it wasn't an exercise you assigned to the class. I think I remember seeing it and being glad I didn't have to do it. Okay, so partition is just that collection of disjoint non-empty subsets. So then the other interesting one is the order relations. So order relations. So it's going to be similar. And it was good to learn order relations with respect to those three properties of equivalence classes. But a relation, and we still use the tilde just abstractly, on a set A is called an order relation. And sometimes it's called a simple order or a linear order, but they always call it ordered sets. And so that would be the application for the order relation. If it has the properties, and then there's going to be three properties here. Now, when you think of order, there's going to be a modification on the reflexivity, and it's going to be considered comparability. So if we have for all pairs x, y inside of A, where x and y are not the same, not being the same, we need to be able to compare them. So the comparability is going to say that either it's going to be x is relating to y in this direction, or y will relate to x. Either one can be true. We just need some form of comparability if they're not equal. Comparability. And then on top of that, because it's a measure of comparability, we don't want to have the issue of two same elements relating to each other. So we're going to make it so that there does not exist any x's in the set such that you'll end up where x is actually relating to x. Okay, so we don't want x related to x if it's like greater than, because x is not greater than x. This would be non-reflexivity. So this is the negation, well, yeah, I guess, yeah, the negation of the reflexive property for equivalence. And then, but interestingly, so transitivity does hold. So again, if x relates to y, so if this is like if x is less than y, and y relates to z, then you'll have x is still relating to z. So we still have transitivity. So for example, if I have the order relation, so when you put together the ordered relation on a set, so I could have, for the integers, is an ordered set together with less than, because it would be true that for all integers, x and y, if we have that x is not equal to y, then x is less than y. Or the opposite, so you can have y less than x. So it's interesting, they didn't, he doesn't adopt greater than as an order operation. So he adopts less than as the order operation, and if you want to indicate, then it's just the switched order. And then for non-reflexivity, if you have integers, then it is true that x, there does not exist any case. So there is no case where x is an integer, where you can have x less than x. So that can never be the case. So that would be non-reflexivity. But the transitivity is pretty straightforward, because if I have x less than y and y less than z, this is actually how we set up the interval notation for open intervals, because then we have x less than z, and he also adopts x less than y less than z at this point, because then he's going to use this to define the open interval using the transitivity.
Okay, he's thinking ahead.
Yes. He's developing, because in light of the Cartesian product discussion that's about to happen. So he has to clear some of the notational issues out of the way.
Did they give an example of a set that cannot be ordered?
Yeah, I didn't see it in the book, but there's also a chance that I just missed it. So I could go back though, because I was interested in looking for, especially with the harmony stuff. I'm going to be digging around anyways out of necessity for an example where if I can get the point or I can have it not ordered, because transitivity is really hard to avoid. But I'm certain this is probably the weak point, because you could probably identify or have some sort of element where its definition is going to always kind of relate to itself. I can imagine there's a case when that'd be true, but I'd have to see. I'd have to play around with that.
An example is the complex number. The complex numbers cannot be ordered.
But they can be dictionary ordered.
Yeah. Okay.
Dictionary order.
Is that defined later?
Yeah.
Okay.
Well, let's see, because it's what I'm gonna get to. I want to get to the integers and the Cartesian products. Okay. But yeah, things get interesting when you start showing on more, because you can dictionary order any set of any like tuples depending on how large you want it to be. You just have an algorithm where you prioritize equality of the things, of the first coordinates, and as you go down the coordinates, that's how you determine. So it's just iterating equivalence relation, then order, then equivalence relation, then order over and over and over again. Yeah. So I'm certain you could do that with complex plane, because you would just have one for the reals and then one for the complex component. I am going to include this just because I thought it was really cool. I never knew really how to express what the integers were with relationship to the reals. So this little short discussion was, I had a lot of fun with this because it took me half an hour over dinner to think about it. But we're going to first define, so if we have some sort of set of real numbers, we're going to call this inductive. If we have, it's true that 1 is in our set, and that x in A gives x plus 1 in A. And so if we have script A be a collection of all inductive sets, or well, I'll call them inductive subset because that more accurately describes what's going on over here. So inductive subsets of R, then the positive integers, so is defined by this union. And like when I thought about it, it's a very, very beautiful definition, very efficient. We're just going to simply intersect all of our inductive sets, because even though this can be a subset of reals, so that could include irrational numbers and all sorts of things, it has to obey these. So those elements are always going to be the ones that are in every single inductive set, whereas you'll lose off all of the negatives, you'll lose out 0, and all that's going to be left. So over all of our inductive subsets, we're going to just be left with 1, 2, and the positive integers.
That's interesting.
So I like this argument better, because then his distinguishing between naturals as including 0 is a lot more, at least it has, there's a reason I want to believe him now, because if you have the intersection of all the inductive sets, you're like, okay, I can accept that starts at 1. But then distinguishing between naturals is then you can start with 0 to count.
Okay, good, I like that.
So yeah, he uses naturals, so then the distinguishing factor is naturals then includes 0. But then the overall set of integers is going to be the union of z plus, or he just takes the naturals with the negatives of 0. So that was, I don't know, I just thought that was kind of pretty
That
because
is
I've never
good.
gone through that before.
Just one thing stylistically, I don't know if he does it, but definitions are kind of always if and only if.
Oh, he left a footnote. So this means if and only if. Yeah.
Okay. So some authors will actually put like IFF. Have you ever seen that?
Mm-hmm.
Okay.
There was a book in the library I found, but that seems to be going away. That seemed like a previous generation convention. Because now authors are too lazy to do that. So they'll footnote the very, very first, or they won't even footnote it anymore. They'll put it in the preface. They'll just say, when you read this book, definitions are logically defined to be if and only ifs. So you can't just have, it's not necessarily a restricted converse or something like that weird.
Okay. Maybe identify the generation by the F's, number of F's.
Oh yeah, no, I got dated so hard by a postdoc. Because I use your set theory filter like notation, and they're like, "What are you doing? Like you're only 20 years old. Why are you writing it like that? That's wrong." Yeah. So I think the way I'm going to use this little last bit of time for the Cartesian product is go through establishing the tuple. So I don't have time to go exactly into every single definition in the middle, but there's plenty of things that I can generously assume that aren't too crazy. So if I suppose that we have a set of sets, so a collection of sets A1 to AM, and J being an indexed set, so it's going to go contain the integers 1 to M. And then we're going to take the union all the way up through with our, so this is, they go through what else, they construct this earlier in the section, but it's pretty straightforward for the purposes of building the Cartesian product. So the PI1 to M or AI is going to be the shorthand for writing out A1 Cartesian products all the way through. And they define a tuple, and a tuple is going to take elements of J and mapping it into elements of X, where every single one of these is going to correspond. Whoops, that's not equals. They need to come from that particular subset. So if it's going to come from like 2, it needs to come from the second subset. This allows every single one of these to be unique. So this is the most general open Cartesian product. There's a few notational things that I recognize are probably a little bit different. So here, conventionally, instead of noting the mapping and then doing it function notation, this is the thing that's where we get at least that's where he's showing where he gets his subscripting notation. So in an index, xi or x alpha or whatever is going to mean a tuple, this mapping of an index set to the union being shorthand. And then this is the formal version of the shorthand, which would just be x1 through xm.
Nice.
So it's a more rigorous depiction of what that assignment really means. So that is kind of nice to have the hardware. He does talk, so this would be an M tuple. And then he extends with this definition of M tuple, it's easier to go up to the omega tuple. Because then you're just saying, instead of J being finite, if I let J be positive integers or the inductive set, now you have the inductive set over a tuple. So we use omega for that, which I think has theological significance just because the mathematicians who put that together with no alpha and omega. And then for Euclidean space, so where we get our M from, well, RM is really communicating in the language of these tuple maps is I want X to take a positive integer, which is now for the entire thing. Well, no, now I think about it. This is the finite case. I'm not doing omega tuple. I did a finite case here, so I'll switch it over so we can talk about both. So our omega is going to be, now we can use the inductive set to the reals. Now, if these were different sets, then we would take the union across all of the sets, but since you have the same exact one and your Cartesian product is the same,
It doesn't matter.
the union is going to be that.
Yeah.
And then every single, I'll adopt the conventional notation here. So xi is real. So that is an infinite sequence. So he kind of hints at sequences as being omega tuples, which was kind of interesting because I hadn't really thought about that for coordinate systems, because usually you would do a sequence as, more of a function, but
yeah, an infinite sequence is an omega tuples.
Yeah. So then I yesterday I was talking with somebody else. So I had a chance to already actually walk through constructing different forms in the different cases for having either finite and different sets, finite same sets, infinite different sets, infinite same sets for Cartesian products. So basically, long story short, this is all the hardware necessary to justify that this notation R2 can be rigorous. In other words, it's going to be all of our tuples x1, x2, where x1 and x2 are real, which is geometrically the point. So, yeah, cool. That's sections 1 through 5, and then I'll probably get through some of the maximal stuff and ordered sets and finite sets.
That's cool.
Yeah.
So it's kind of stuff that most people that take it would be familiar with, but rephrased in the language that he wants to use going forward.
Basically, that's what it really felt like.
Yeah.
It felt like getting used to what words he was going to be using in the future chapters, but it's pretty much the same. There's very few things that are different other than the functions, right.
But little nuggets of interest in.
Yeah.
But what's your name?
My name is Moses.
Moses.